Just to remind you guys, we're finishing up section 7.6, but you guys are now getting into the real heart of the pumping liquid out of tank problems. And then right after that, we do pumping liquid out of a bunch of different kinds of tanks. And then the next thing we're going to do is something called the center of mass or centroids. And then that will be it for chapter 7.6, which means time for test, time for homework sets and the like. So I want you to notice down here at the bottom, your homework number 5, test review number 3, it will be due next Friday, March 29th by 2 p.m. at our review session in Fretwell 113. And also to remind you, today's Friday, we got a review session at 2 o'clock in Fretwell 113. So if you've got questions on web work, you've got maybe even questions on this thing, we don't mind taking a look at this guy with you guys a little bit at this if you want to bring it along. And so review session today, but next Friday I will be covering the review session in particular because I will be making a video of the solutions for this guy for this homework sets for you guys, which also means if the test is on Friday, the homework set's due on Friday, that means your test number 3 will be on Monday. In this case, it will be April 1st. So let you guys know everything's set up. We're actually right on schedule with our syllabus, which is highly unusual. So pay attention to this. Here's your homework set. And just like before, you're going to print this thing out. You're going to do the entire homework set, and you're going to enter your answers on Canvas. And at the review session, the only thing that I really want you guys to turn in is the free response questions. But at the review session, I'll cover the entire homework set in its entirety, but you only have to turn in the free response part 2 of the homework set. It looks just like the test that I eventually will make up, be there before next Monday and stuff. So there we go. All right. Let's talk about what we did last time. We got through one good problem last time of a tank where the problem is the tank has a slant on the side. It's not completely vertical. The vertical tanks are the easiest ones of all because it doesn't matter where you make the slice. That little change in volume is going to be the same for every slice. Our problem is going to be when the tank has the side that's on a slant or some type of equation that defines the slant. And that equation that defines the edge of the tank is the relationship between the x and y variable. You'll have to come up with that equation. So, just to remind you guys, the formula for doing tank problems is going to be work is equal to the sum of the delta force times the distance you have to pump. The delta force is equal to water weight times your delta volume slice. Now, water weighs either 9,800 newtons per meter cubed if you have the metric system, or 62.5 pounds per foot cubed if you have the English Standard System. If I give you some other type of liquid, oil, gasoline, hot chocolate, which is what a WebWorks is going to do for you guys. Traditionally, we're going to do that one in the metric system where we give you the density of whatever liquid you're playing with. You multiply it by 9.8 to get that liquid weight that you'll use right here. Your delta volume slice, remember when you make a slice, you're going to make 1 or 2 different slices. It's just going to be disc shape or it's going to be box shape. Now this one is a inverted right cone. So when I make a slice through this inverted right cone, it actually makes the shape of a disc. It is a cylinder. So the volume of that is going to be a straight up pi r squared h. The h is always going to be the delta y. But the problem in this one is your radius. The radius changes on where you take your cut at. At the top, it's all the way up at 4. At the bottom, it's 0. So it's somewhere between 0 and 4. It varies. But anytime you move away from the y-axis, it's going to give you an x coordinate. The radius is x. So you get the pi x squared delta y. That'll be your delta volume times your water weight, 9,800. So you get work is equal to the delta force times distance pumped. That's the sum of 9,800 pi x squared delta y. That's your delta force part. And the distance you have to pump is from this arbitrary y level that you made this slice up to where you want to pump all the liquid. In this case, it was 15, so it's 15 minus y. And then I cleaned this equation up, summation into integration. delta y into dy, and I got an equation, but I got a big old problem. And that problem very simply is I got an x in the middle of my dy. You're going to have a lot of this. What you need to do is come over here and find the equation for the edge of the tank. In this case, it was a line. So for the equation of the educate line, I used the point slope formula. I had to plot points and calculate the slope, and I used one of my points, and I got the equation of the edge of the tank is y equals 3x. Remember, this purpose of this equation for the edge of the tank is to substitute in for x to turn it in terms of y. So if y equals 3x, that means x is equal to y divided by 3. And so for that x, I plug in y divided by 3 squared, and then I just set up my bounds. And remember, you integrate over what your water you're removing. In this problem, they said remove all the water. The water in my tank, based upon my coordinate axis, is between 0 and 12. So I integrated from 0 to 12 of that y over 3 squared times 15 minus y, and got my solution. So let's do another problem. Now, I'm always trying to come up with ways of coming up with the formulas, make them easier. And you can use the little formulas because there's a pattern on these things. But traditionally, I'm going to set it up in my classic summation formula. And you'll see that these are actually the parts of the formula. Now, the problem is you're either going to have a circular cross section or you're going to have a box shape. Let's take a look at this one right here. It says this: a trough shaped tank has dimensions of A is 4 feet. And so down here at the bottom, here's A. This is going to be 4 feet. The B up at the top is 8 feet. The height is 12 feet. And the distance is 20 feet. Now, this is a straight distance on this one. Okay? So what you got here in this trough-shaped tank is we got the cross section is a trapezoid, and you got a 20-foot distance on the thing. And this tank is completely full of water. In this problem, it says, find the work done in pumping the water out of the tank to over the side of the tank. All right, so first thing you always want to do on any tank problem is you've got to draw the coordinate axis. And you look at it from a cross-side, a cross-section perspective. The cross-section of this tank is the trapezoid. So I'm going to put my coordinate axis at the bottom. The base at the bottom is 4. I like to do symmetry, so right down the middle. Here is 0, and if it's 4, it'll be 2 on the left and -2 on the right. So here's a couple of points that my tank is cross-section. The height is 12, so up here on the y-axis, I'm going to put 12. But then your width across the top is 8. Using symmetry right across the, putting the y-axis down the middle of this guy, half of 8 is 4. So over here at 4, 12, I'm going to hit a point. And over here at -4, +12, I'm going to hit a point. And this is my cross-section trapezoid of the tank. And then drawing in the three-dimensional aspect of this guy, using a little freehand artwork here. The width of this tank is 20 feet wide. Does that make sense? And it's full of water. So to calculate work is equal to the sum of the delta force times the distance that you're going to have to pump. Your delta force by formula is equal to the water weight times your delta volume slice. In this example, pay attention to units. What are you going to use for your water weight? All the distances are measured in what units? Feet. So what is water weight in the English system? 62.5. So this will be 62.5 pounds per foot cubed, things we have memorized, times my delta volume slice. Now to do my delta volume slice, this tank is full of water over here. I'm going to come over here somewhere on my y-axis and make a little delta y slice. Now, you have to envision the slice. So here comes that engineering, physical, mathematical mindset of being able to look at things and see what's going on. If I make a slice through this tank, what's it going to look like? So I'll make this little slice. And I pull it over It's, in this example, is going to be box-shaped. It is 20 feet long. The width of it didn't change. It is delta y tall in this little width. The question is, how long is it? Okay? Well, the fact of the matter is that this thing is on a slant once again. So at the bottom, it is exactly 4 feet wide. At the top, it is 8 feet wide. So it's somewhere between 4 and 8 feet. It varies. So here's the trick. To figure out the variable, we're moving away from the y-axis. Catch a pattern. When I move away from the y-axis, what direction am I going in? X. But because of symmetry, this would be an x distance. And over here, I need the entire length of it. This would also be an x distance. So what is the total distance between these 2 points? 2x. See, this is a box. I need the entire width. When I had a disk, all I needed was the radius, which is the half the distance from the middle to the outside edge, which we just used arbitrary x. But for this one, I'm going to need to use 2x. And being a box, your delta volume slice is going to be length times width times height. That would be 2x times 20 times delta y. That makes it 40x delta y. So I get to put that over here, 40x delta y. Cleaning it up, that makes my delta force equal to 62.5 times 40 is 2,500 x delta y. Now, to finish up my formula for work, work is equal to the sum of that delta force, which is 2,500 x delta y, times the distance, this is your delta force, times the distance that you have to pump. Again, the distance I have to pump. This level that I made a slice at was at an arbitrary y level. Where are we trying to pump this liquid to? They said pump it to the top of the tank. Relevant to my coordinate axis, where's the top of the tank at? 12. So what's the distance I'm going to have to pump? 12 minus y. Does that make sense? Questions? Now, converting this to integral calculus. Work is equal to 2,500 is a constant. Pull it out front. Summation turns into integration. Your variable is x times your function 12 minus y, and the delta y turns into a dy. So I'm almost got my equation, but once again, I got a problem. Okay? What's my problem? I got a big old x in the middle of my integrate dy. Does that make sense? So, here we go. To be able to get that x out of the thing and to convert it into y, I need the equation for the edge of the tank. Equation for edge of tank. And I like the edge of the tank being in the first quadrant, so I'm going to focus there. This right here. And what do you see? I'm going through the point 2, 0, and the point up here happened to be 4, 12. So I'm going through the point 2, 0, and 4, 12. Does that make sense? And what kind of an equation is that guy right there? Once again, it's a line. So to find the equation of a line, I got to find my slope. The formula for slope is 12 minus, changing y over the change in x, that'd be 12 minus 0 over 4 minus 2. That's 12 divided by 2, which is equal to 6. Does that make sense? Now I'm going to use the point slope formula. Y minus y1 equals m times x minus x1. Pick a point. I like the point 2, 0 because of smaller numbers. Plugging it into my equation, it'll be y minus my y coordinate, which is 0, equals my slope, which is 6 times x minus 2. Solving for y equals 6 times x minus 2, or y equals 6x minus 12. That's the equation of a line. And that equation of the edge of the tank is your linking variable equation. But the purpose of this equation is to replace that x in terms of y. So to replace that x, I need to solve for x. So solving for x, the distance the line is away from the y-axis there, x, let's see here, I would add 12 to both sides. That gives me y plus 12 equals 6x. And then I would divide both sides by 6. And I get x is equal to parentheses y plus 12 divided by 6. That is what x is. So I'm going to take that, and now plugging it in for x here, I'm getting the equation work is equal to 2,500. I got too many zeros there. 2,500 times integral of x, which is y plus 12, divided by 6 times 12 minus y dy. And the last thing I need to have is bounds. Remember what I said. You integrate over what you want to remove. Look at your tank, and where's the water we want to remove? We want to remove all the water out of the tank. Where's the water at? Between where and where? 0 and 12. Your bounds are between 0 and 12. Does that make sense? Now, if I want to integrate this thing by hand, I could take that constant and move him out front, FOIL this part out with the y minus 12 times the 12 minus y, and then integrate each term, plug fundamental theorem, plug in top, plug in bottom. But again, this section is really big into setting up the integrals that actually calculate whatever you want. So this would be definitely one of my answers I would be looking for. And then the last thing is, I would tell you to use your calculator to integrate. So I'm going to do it just exactly the way I see it. 2,500, math number 9 integral from 0 to 12 of parentheses x plus 12 close parentheses divided by 6. I'm going to hit times another parentheses because this is not on the 12 minus y is not in the denominator, it's in the numerator, so hit times. And it'll be 12 minus x close parentheses dx. And what do I get? Work is equal to 480,000 watt, foot-pounds. And there's my solution. Now, for most people, they look at this problem and see how much work was required to do the work problem, and they get kind of scared. Because I notice out there, a lot of you guys aren't taking notes on the stuff I'm doing up here. That's your mistake, because you will not pass this class. You have to study this stuff, and you need to sit there and look at the patterns that we're doing each time. There's a huge amount of patterns with this material. And look at how much what we're doing here. And these, I can tell you right now, there's going to be one of these kind of problems on your final exam. There usually is. And we basically just throw it at you guys and say, hey, find the work done. And it's amazing to me, because I'm usually the poor sap that has to grade this particular problem on the exam. And I'm amazed at me of how many students actually leave this problem blank. I don't know what to do. I don't even know how to start the problem and stuff like that. I'm doing the same thing over and over again. And those people never pass calculus 2. They'll take it 3 and 4 times. It's kind of embarrassing. But the fact of the matter is, you got to work at this stuff. It doesn't come naturally. I don't care how good a math student you are. You got to practice this stuff. And we're setting you guys up for engineering, for computer science, for math majors, physics majors, chemistry majors. All different varieties of STEM education up here. This is not easy stuff. It is difficult stuff. But you got to catch patterns, and you got to know what you're doing. So I'm actually doing algebra over here and coming up with the equation of the edge of the tank. I am doing concepts of integral calculus where I'm taking a summation formula and then applying summation to Riemann sums to create the integral form for it. And then I'm using the same techniques of how to put all the parts together. There's a large amount of work going in this thing. But if you do enough of these problems, this is why we give you so many of these problems, we do this stuff every time, the same type of procedure. Does that make sense? This is not difficult, but it is tedious because there's a lot of work to be done to be able to do a problem like this. Take a look at the next problem. it requires your math knowledge. So you're going to have to put a lot of stuff back from your high school math classes back into this. Take a look at this one. It says this: a hemispherical shaped tank has the dimensions that the radius is 10 meters, and the tank is completely full with finding the work done and pumping all the work out of the side to a distance of 2 meters above the top of the tank. Now, the hardest part and the first thing you got to do on any kind of problem like this is you got to visualize it and put your coordinate axis on there. What is the cross section of a hemispherical tank? What do you see in terms of your cross section? What is this thing? Just kind of mash this thing together and tell me what you see on a two-dimensional sheet of paper. What do you got? It's a semicircle. All right, and I told you guys before. Now, there's lots of different ways to do this problem, and you can put your coordinate axis anywhere you want to. We're all going to get the same answer as long as you do it right. But if I'm doing a problem that the cross section is a circle, I don't put the coordinate axis at the bottom. To make the equations a little easier for me, I put the coordinate axis in the middle, and you'll see why in a second. So on this one, I have a hemispherical tank. Okay? And the hemisphere is, honestly, it is half a sphere. So I'm going to dot this thing up here. But, and as I mentioned, this is the cross section is a circle, and on a circle, I'm going to put my coordinate axis in the middle. And here is where my tank is. It's at the bottom. So what was the radius of this tank? It was 10 meters. This will be -10. It'll be -10 down here. And it is 0 right here, because I'm putting my coordinate axis at the top of the hemispherical tank because it puts it in the middle of my semicircle. Does that make sense? But now, where's my target at? My goal is to take this thing as a hemispherical tank. So now you can draw your little three-dimensional aspect of this guy. So there's your hemisphere right there. But you want to pump all this water where? To, what was it? 2 meters above the top of the tank. But because I put my coordinate axis at the top of the tank, and my coordinate axis is 0, the 2 meters above that would be at the level what? 2. And this is my target. I want to get the water to the level of 2 relevant to my coordinate axis. Now, here we go. Work is equal to the sum of the delta force times the distance you have to pump. Delta force is equal to water weight times your delta volume slice. I do the same thing over and over and over again. You got to memorize these formulas. Now, let's start calculating this thing out. So to calculate my delta force, what does water weigh in this problem? 9,800 newtons per meter cubed. 9,800, because this was a metric problem. All my distances were measured in meters. Does that make sense? The next thing is this. What's my delta volume slice? And what's it going to look like? Your delta volume slice. When I go over here and where the tank is at, and here's the top of my tank right here, somewhere in the middle of my tank, I'm going to make a little delta Y slice. And if I slice this hemispherical tank through and I look at it, what kind of shape am I going to get out of this guy? And if I pull it out, it's going to be a disc. Now, I know a lot of people sit there and go, wait a minute, Dr. Taylor, because of that slant on the side, is it actually disc shape or is it going to be a little rounded on the side? Delta Y is so thin of a slice that we're making, it don't matter. The delta Y is the height, because you're making actually, and think about Riemann sums, an infinite number of slices. This is just one of an infinite number of slices I'm going to make through this thing. So you're making literally the poker chips that we're going to stack on top of each other to make my hemisphere. It doesn't matter what the edge of the tank is at this point. When you make a slice and it's paper thin slice, it's either going to be disc shaped or it's going to be box shaped. You only get 2 shapes out of this thing when you make your slice. So your delta volume on this is going to be pi r squared h. I ask you, the height is delta y. What would my radius be? Tell me. It's not vertical, it's on a slant. Does that make sense? And because it's on a slant, when you move away from the y-axis, what direction are you going? X. Catch a pattern. So your radius is equal to x. So your delta volume is going to be pi x squared times the height, which is delta y. and that is your delta volume, pi x squared delta y. So now that you got your delta force, now write your work formula. Work is equal to the sum of that delta force, and your delta force is 9,800 pi x squared delta y times the distance that you got to pump. What is the distance we're going to have to pump? Well, my target is to lift all this water, and that little slice of water that I was analyzing right here, I got to lift it up to 2. Now, this slice I made was at an arbitrary y level. I've got to lift it. Work is all about lift. So what's the distance I have to lift this arbitrary y level? 2 minus y. Does that make sense? Now, convert this into integral calculus. Question. Where did I put my coordinate axis at? It's all about the coordinate axis. The top of the tank is at 0. The bottom of the tank is at -10. So I am going to be integrating over negative numbers on this one. And I'll show you why I chose negative numbers on this one in a second. But because I put the coordinate axis at the top of the tank, and the coordinate axis, the origin, is at 0, and that's at the top of the tank, that means 2 meters above the top of the tank is going to be at the level 2. And it's 2 minus y, but my bounds will be negative, okay? So, and I'll explain why in just a second. So here we go. Work is equal to 9,800 pi is a constant, goes out front. Summation turns into integration. There's my x squared. There's my 2 minus y, and my delta y turns into a dy. And I got the same old problem when you have a tank that has an edge that is a slant. So I've got to come up with, and this is the big deal, the equation for the edge of the tank. Question for you. What does the edge of the tank look like? What is this thing? What is your cross-sectional look at this guy? It was a hemisphere, a semicircle, right? Cross-section. But so it is a circle. And I chose to put the center of the circle centered at the origin, 0, 0. Do you guys remember what the equation of a circle is centered at the origin? Hey, you got it. What is it? X squared plus y squared equals r squared. If you did not want to center it at the origin, you could have used the awesome equation of x minus h squared plus y minus k squared is equal to r squared. You could use the original standard equation of a circle, which is the centered at hk, x minus h squared plus y minus k squared equals r squared. But trying to manipulate and solve for x in this equation, royal pain in the butt. So this is a little bit easier. What was your radius of this particular tank? 10. So this would be equal to x squared plus y squared equals 10 squared. So x squared plus y squared equals 100. And I'm trying to substitute in for an x squared. So I actually don't have to solve for x. I need to solve for x squared. So solving for x squared on this particular problem, subtract y squared from both sides, I get x squared is equal to 100 minus y squared. And I can take that and plug it in right in here. That gives me work is equal to 9,800 pi times integral of your x squared, which is 100 minus y squared, times 2 minus y dy, and all I got to do is figure out the bounds. But because I put my coordinate axis at the top of the tank because it was a hemisphere, my bounds are between what? Where is the water at in this tank? Relevant to my coordinate axis. Where's it at? From -10 to 0. I'm integrating it from -10 to 0. Does that make sense? Now, if you decided you wanted to sit there and put the tank at the bottom, the coordinate axis at the bottom, that's fine. You could have done that, but you would have had an equation. So let me just kind of show you what we're talking about here. If I put the axis at the bottom, I'm drawing the circle, but remember, it's just a hemispherical. There's where the water's at. This would have been the equation. This would have been the center of this circle is right here, and the center would have been at the point 0, 10. So you would have had the equation of a circle, x minus 0 squared plus y minus 10 squared is equal to your radius 10 squared. So you get x squared plus y minus 10 squared equals 100, okay? And that's fine too. And then your work would have been pretty much the same formula except for this. The top of the tank, if this is at the point 10, your target would have been 12, as you were mentioning earlier. Then you would have gotten the equation 9,800 pi times integral from where the water is, from 0 up here to 10, 0 to 10, of solving this guy for your x squared. It would have been 100 minus, parentheses, y minus 10 squared, parentheses around that, times the distance you have to punch will be 12 minus arbitrary y, 12 minus y dy. And this would have been what your equation looked like if you wanted to center it not at the origin. Watch, we'll get the same thing. Question, yeah?
Why is a semicircle give you a cross section of a circle, but it comes into a box?
Okay, now, well, hold on. Interesting question. I shall bring back the pages of time here. All right, cross section, when I slice this thing, gives you a little disc. Is that what you're talking about here? Yeah. Okay. Well, you're talking about cross-section equations or cross-section when I make my slice? Okay, the slice. Okay. And you get a little circle out of it, right? And when I slice this thing here, your cone, when I slice it, it's still circular, right? Because it's a cone, and I'm going to get pretty much the same picture. The only difference is this one, I mean, I'm making this really much thicker than it is. It's paper thin, right? But it is still very thin, and it's because you make a cut right across a cone, you're going to get a circle. You make a cut right across a semicircle, you're still going to get a hemisphere, you're still going to get a circle. But when I actually crossed over this one here, when I crossed over the, what did I call this thing? A trough, there it is. When I made this cut, I cut it out, I made a box. So now, let me just actually use our calculator to integrate, and I just want to show you this. So I'm leaving the answer in terms of pi. So I'm going to put the 9,800 times math number 9 integral from negative 10 up to 0 of, parentheses, 100 minus x squared, close parentheses, times 2 minus x, close parentheses, dx. Now, honestly, I would have chosen this method, especially if I want to integrate it by hand. I would FOIL this part out and then just integrate each term. That's not too bad. But what do I end up getting when I do that? I get an interesting work is equal to, let's see what we got here. What is that? 37 million. That's awesome. 566,666.67 pi watt. Joules. Don't forget your units. It's a physics class. Now, if I decided to do it this way, that's awesome. I just want to show you, leaving the answer in terms of pi. I'm going to put this in the calculator. But look at how much algebra you would have to do if I told you to integrate this thing by hand. You would have to FOIL out the y minus 10 squared, then subtract 100 from it, then FOIL that times 12 minus y. A lot more algebra just to do it by hand, you understand? But I'm going to stick it on the calculator, so it's 9,800 times math number 9, the integral, from 0 to 10, just to make those bounds positive, but it would be parentheses, 100 minus parentheses, x minus 10, close parentheses, squared, close parentheses, open parentheses, 12 minus x, close parentheses, dx. All right, so I'll type in exactly the way it looked. Let's hit enter. What do I get? Oh, yeah, I get the same answer because that's called math. So does that make sense? It doesn't matter which way you do it, but personally, I like this method a little bit better than this one because it makes if I had to integrate it by hand, centering any kind of cross section that's a circle, centering it in the middle of that circle makes your equations a little bit nicer, which will make your integral by hand a lot nicer. Does that make sense? That's why I choose. But it does make me have to integrate over negative bounds. Let's look at this one. This problem here is the one that I came up with a few years ago when the department asked me to be on the committee to make up the final exam. It's one of those rare semesters that they didn't make me teach Calculus 2. So when they don't make me teach Calculus 2, they put me on the crappy committee to make up the final exam for Calculus 2 exam. So this is one of the questions I made up. So to let you know, I also just took it and put it in our notes as well. But this is one of the examples that I made up for our students. So let's see if we can do this problem. I tried to come up with something a little more interesting. So I said a tank in the shape of a triangular prism has the following dimensions. The height is 15 meters, the length is 20 meters, the width is 10 meters. The tank is filled to the top with water. Find the work required to pump all the water out of a tank to a height of 5 meters above the top of the tank. All right. So the first thing you got to do is you need to look at the cross-sectional area of this guy. I've got a triangular prism-shaped tank. What's my cross-section look like? It's that part right there. What is that? And it's a triangle. So my cross-section is a triangle. Okay? Where would you put your coordinate axis if you're making triangles? That's the key right there, because that's what we're looking at. If you don't draw a coordinate axis on this thing, you'll never get the problem right because we don't know how to grade it. I'm talking about from the committee who has to grade this crap. We have to look at the coordinate axis because that sets up everything. Where you put there's only one answer. We'll look at the answer, but in terms of partial credit and looking at the work and stuff like that, it's got to match to your answer. You've got to show me where the coordinate axis is at. Personally, since the cross-section is not circular, I'm going to put it at the bottom. It's easier for me to explain, and the equation is going to be just as nice. So I'm going to put it at the bottom down here. There we go. So let's take a look at our dimensions on this thing. It says that the following dimensions. The height, B, is 15. So this makes up here at 15. The length is 20, so I can actually put the three-dimensional aspect of this guy. This is 20 meters. Let's see here. And the width is 10. The D is the width. That's across the top. So if it's 10, and I put my y-axis down the middle, this will be at the 0.5 and negative 5. Does that make sense? And then just equally important, the tank is full with water to the top. Find the work required to pump all the water out of the tank to a height of 5 meters above the top of the tank. Look, where I put my coordinate axis, where is 5 meters above the top of the tank? Where's my target to get the water at? 20. So up here at 20, 5 meters above 15, the top of the tank, this is my target. I got to get the water to 50, to the point of 20. So once again, work is equal to the sum of the delta force times the distance that you have to pump. Delta force is equal to water weight times your delta volume slice. In this problem, what does water weigh? What constant are you going to use? Again, I measured this one all in meters, so it is 9,800 newtons per meter cubed. It's the density of water, 1,000 times gravity, 9.8. That's where the 9,800 come from. Times my delta volume slice. Now come over here, somewhere on an arbitrary inside my tank, I'm going to make a little delta Y slice, and I'm going to slice this guy, and I'm going to envision cutting all the way through this tank and pulling that little section out. And what does it look like? Because of this prism-shaped thing here, it's going to look like a box. It is delta Y tall. It's 20 meters long because I made that constant. But hey, the question is, how wide is it? Catch a pattern. How wide is it? Yeah, exactly, 2x. And the reason for the 2x is because the edge of the tank is once again on a slant. So when I move away from the y-axis, I have to go in the x direction. Because of symmetry, I'll go in the x direction the other way. So the grand total length of this box is going to be 2x. So your delta volume is equal to length times width times height. This is going to be 2x times 20 times delta y, or 40x delta y. And that comes here, 40x delta y. So to clean up my delta force, just putting my constants together, and nasty, but they're big numbers here, I'm going to end up getting 9,800 times 40. And that gives me 392,000 x delta y is what my delta force is. Now, continuing and catching patterns. Work is equal to that sum of delta force times the distance that you have to pump. This would be the sum of 392,000 x delta y times the distance I'm going to have to pump. This slice that we made was at an arbitrary y level. I've got to lift the water to 5 meters above the top of the tank. Where was my target? 20. So what's the distance I have to pump? 20 minus y. Does that make sense? Converting it to integral calculus, this is going to give you the integral of 392,000 x times 20 minus y dy. The delta y turns into the dy, and the summation turns into an integral. Now, I got the old problem, same old problem. I got a big old x in the middle of my integrating with respect to y. So now I got to come back and come up with the equation for edge of tank. What's the equation for the edge of the tank? Well, the edge of the tank is what shape in this one? It's a line. What points did this line go through? Because I set it up at the bottom, try to make it nice for you guys, it goes to the origin, 0, 0, and this point on the quarter of the tank goes to the point 5, 15. So my slope, which is the change in y, y2 minus y1 over x2 minus x1, would be equal to 15 minus 0 over 5 minus 0, change in y over change in x, that's equal to 3. Now I'm going to use the point slope formula, y minus y1 equals m times x minus x1, and I'm going to use the points, because I had 2 points here, 0, 0, and the point 5, 15. I could use either one, honestly, but I got a brain. I'm going to use the point 0, 0. So there'll be y minus 0 equals my slope of 3 times x minus 0. I mean, sometimes you can even look at this thing and tell what the equation is. Y equals 3x. It's a line. But what's the purpose of this equation of the tank, this edge of the tank equation? It's your linking variable equation. I'm trying to get rid of that x, so I'm going to solve this equation for x. So as y equals 3x, that means x is equal to y divided by 3. X is the distance away from the y-axis. So if I ask you, what's the equation for the distance away from the y-axis the edge of the tank is, it's x equals y divided by 3. I'm going to plug that in right in for x. This gives me, cleaning it up, 392,000 integral of x, which is y divided by 3, times 20 minus y dy. And the last thing I got to do is figure out my bounds. Where's the water at that I'm trying to pump out? Once again, things full of water, get all the water out. Where's the water at? 0 to 15. Not 20. 20 is where we're trying to get the water to. There's no water here. The water is actually in the tank from 0 to 15. This is the equation that sets up the work. And to actually get your answer on this problem, this one actually is very doable for integrating by hand. All I have to do is distribute. I could actually pull the 3 out front, the 1/3 out front as, and distribute the y, and it's something you can actually integrate by hand. But again, to save time, I'm just going to use the calculator. 392,000 times the integral of, and I worked real hard to come up with a problem like this. Integral from 0 to 15 of parentheses x divided by 3 times 20 minus x dx. And what do you end up getting for an answer? A very nice let's see here, double checking. Yeah, 147 million what? 147 million joules, because this was in the metric system. Does that make sense? Question, yeah? Yeah. I mean, I could. I mean, it's not going to be actually, on this particular tank, you could put the coordinate axis at the top if you wanted to. It's just going to make your equations a lot nastier, but there's only one answer to this stuff. I mean, it's the beauty of math. And there's like 14 different ways to look at it. So when we're doing these problems, the first thing we're going to do is we start giving you points. If we don't see a picture, we know you lied. Okay, you've got to draw a picture on this thing because your bounds and everything is based upon the coordinate axis you set up. So when you don't set up a coordinate axis on this problem, you're making up numbers to put in this thing because you got to show me where these numbers come from. You got to have your coordinate axis, and you can put it at the top. You could put it up up there at 100 if you want to, integrate over a bunch of negative numbers. But at the end of the day, there's only going to be one answer, and if you did it right, you'll get the right answer on it. Okay? So, and again, we are not going to typically specify where you have to put your coordinate axis on the exam or my test or the final exam. We just give you a work problem, but we're looking for these parts to actually grade by. So there's a lot of things going on here. So there is a lot of partial credit we're looking for. We're looking for the equation of this, the picture, excuse me. We're looking for your formulas and you plugging in. We're looking for your delta volume slice, plugging it in. We're looking for your target. And then we're looking for the actual, at the end of the day, we're going to ask you, what is the integral that sets it up? And then sometimes we'll say integrate by hand, other times we'll say use your calculator to integrate and for the answer. And again, last thing we'll check was units. Now here's another problem right here. And this is more of a reality problem than anything else. But it is much more difficult. This is one I'm definitely going to get you guys to use your calculator to integrate. All right, here's the deal. The tank in the shape of a cylinder on its side, see figure below, has a dimension that it has a height of 15 meters, has a radius of 5 meters. And the height, because it's on the side, is right here. So this is 15 meters that has a radius of 5 meters. And the tank is, in this case, full of water. Find the work done required to pump all the water out of a hole, and I even put the hole up there for you, on the top of the tank. That's where we want to get the water in. So to give you guys a little reality check here, we're here in North Carolina, so that makes us very nice because we got all kinds of different ranges. We got the mountains to the west of us. We got the coast on the east of us. And if you go down towards the coast and you look at gas stations, for example, the water table in the eastern part of the state is so high that you can't bury anything. So when you go to a gas station, what you're going to see behind the gas station is a bunch of tanks, and they typically are going to be in a cylindrical type shape. Sometimes they put little round caps on the end of them, some of that, but they're going to look like this. And you actually get to see where the gas is being stored at, and they're typically behind the gas station. But over here in the western part of the state, we're up on sea level quite a bit, so we got a lot of ground underneath us. So to make things look more pleasing, what do? We dig big holes in where these gas stations will be, and we put the tanks under the ground. So you don't actually see the tanks. You see the big 18-wheeler dropping off and then pumping some gas into a hole in the ground. But underneath that hole is a big old tank. It's the same kind of tank. It's typically a cylinder on its side. And why do they put it on the side? It's because you don't have to dig as deep when you have it on the side versus a tank that looks like this. I mean, that's a nightmare in terms of digging that kind of hole, 20 meters down and whatever. So you may end up hitting water by that time. But on this side, putting a tank on the side, you've got enough ground underneath you before you hit your water table that you can put it like this, and it looks a lot cleaner over here at the western part of the state than having these tanks behind the gas station in the eastern part of the state. Just FYI. So you want to figure out the work done in pumping all this water out of the tank. What's the cross section of this thing? What is the cross section of a cylinder on its side? What is it? Cross section is a what? Circle. And because I have a circle, where would I put my coordinate axis? In the middle of the circle. That's going to make the equation a little bit nicer. What is the radius of this tank? It has a radius of 5 meters. So this would be 5, 5, negative 5, 5, and it has a length on it of how long? 15 meters. Okay? I'm gonna finish this problem up next time, but I want to just set this thing up. And we're gonna pump the water to a hole in the top of the tank. But I just wanted you to see what this thing is gonna look like. But one last question before I let you guys go. If you make a horizontal slice through this tank, what does it look like? It's a box shape, right? It's not gonna be circular because you're slicing it this way. It's gonna make, when you make your little slice, it's gonna be a box shape. Let you guys know. We'll study this problem next time, and then we will get into the, quote, center of mass problems. The last section, last part of section 7.6, which they have a special web work on this one. See you guys then.